real gases. So today we're going to look at real gases, and so far we've treated every gas as if they're ideal, but today we're going to deal with a situation where we don't make that assumption. So we need to do this because ideal gases don't exist. We started this, we said that ideal gases, we made a couple of assumptions about ideal gases. First, we assume they don't take up space. But molecules really do take up space. They have a size. Heck, earlier this year, we saw how the size varied, how atoms varied in size on the periodic table. Atoms take up space, so the molecules actually have to take up space. We can usually ignore it because the molecules are so far apart. But we know that there really is a space for those molecules. We also assume there's no attractive forces, but there are attractive forces. Because if there weren't attractive forces, there wouldn't be any liquids or solids. Everything would be a gas. If the molecules never stuck to each other, you'd never condense into a liquid. So when do real gases behave like ideal gases? When does this work? Because we know when it works, we know when it doesn't work. So real gases behave like ideal gases when the molecules are far apart. Now these two boxes over here, it's not that it's the same molecules in two different boxes. So there's the same number of molecules in both boxes, but in this box they take up much less space, much smaller percentage of the space because they're spread out further. So when the molecules are far apart, they take up a smaller percentage of the space, and ignoring their volume is reasonable. Ignoring the space the molecules take up in here is much more reasonable than ignoring the space they take up in there. So what can we measure that would tell us that they were far apart? Well, if they're far apart, they're not going to hit each other or the walls as often. So this is going to happen if the pressure is low. So the lower the pressure, the more ideally the gases behave. The higher the pressure, the less ideally. Ideal gases behave like real gases. Real gases behave like ideal gases when the molecules are moving fast. And why would moving fast make a difference? Well, then they're not next to each other very long. And if they're not next to each other for very long, they can't stick to each other. So the faster they're moving, the less that attractive force plays a role. So think about what could I do to make them move faster? Well, of course, raise the temperature. So if the temperature is high enough, they behave ideally. If it's low, they don't. What do I mean by high temperature? Well, high temperature means a long ways above its boiling point. Because near its boiling point, it sticks together so well that it's not going to come apart. That's where it's going to stick together and make a liquid. So you got to be far away from the boiling point. And there's a couple of graphs that show you how it really gets affected. Okay, so this is a graph of PV over RT. So PV over RT is N. So they set it up so PV over RT was 1. So 1 mole. And for an ideal gas, no matter what I did to the pressure, PV over RT would always be 1 mole. But there are, oops, sorry about that. Okay, so let's look and see where it varies. So initially I start off by dropping down below the line. So down here, my answers are too small. And the reason why they'd be too small is because I'm increasing the pressure and the molecules stick together. I'm pushing those molecules closer and closer together so they're going to stick. The closer together they are, the more they're going to stick together. And then, once you reach a certain point, it increases. And that's because you've squeezed them together so close that the molecules are taking up a bigger and bigger percentage of the space. Now, these look like huge variations, but look at the units we have here at the bottom. That's pressure in atmospheres, and these go up by 200 atmospheres a time. So we are not going to be at 200 atmospheres very often. We usually work in this range down here, down near the single digits atmospheres. So that's why it tends to work pretty well for us. Here's a graph where instead of doing different gases like they did in the last one, they got PV over RT equals 1 again, that part, and it's got the pressure changing, but now they did it at different temperatures. The last one was all at different temperatures. And as you can see, they all have that same drop pattern, but the higher the temperature, the faster it starts moving upwards. The fact is, at 1,000 Kelvin, you can't even see it drop below at all. So the higher the temperature, the better it works, especially if you're down here where the pressure is low. Okay, and so that's the faster they're moving, the less they stick to each other, so the more closely they approach the ideal gas. So which set of conditions would a gas behave most ideally? We answered this before. Let's check and make sure you still remember which one it is. So you'll notice that I have to choose between 1 and 2 atmospheres. When does it have better? At low pressure, high pressure? Well, the lower the pressure, the better, so I'm expecting it to be 1 atmosphere. And now I got 500K or 50K. Works better at high temperatures, so 500 is bigger. So it's going to work better at 1 atmosphere and 500K, and it's going to work the worst at 2 atmospheres and 50K. Okay, so what do we do? What do we do if we're going to treat them like real gases? We can't use the ideal gas equation, so they came up with a different equation. And the equation is called van der Waals equation. And van der Waals we've talked about before because van der Waals forces were those weak intermolecular forces, the dipole interaction and the dispersion force. So van der Waals studied those weak interactions. And he realized he had to correct for 2 things. He had to correct for the pressure, and he had to correct for the volume. Correct for the pressure because they're not hitting the wall because they're sticking, and correct for the volume because the molecules take up some of the space. So here is what it looks like when you do that. So it says POBS. OBS means observed. That's what the meter is going to say. So what pressure do you read off the meter? Because the pressure you read off the meter needs to be corrected. Okay? And so we're going to correct it by adding this term. And it's got N moles, it's got V, and then it's got this A. Well, A is a number that depends on how much they stick to each other. So the more stickier they are, the more my observed pressure needs to be increased. So I add to it. And B is a number that's determined by how big the molecules are. So I've got the volume of my container, and I have to subtract away how big the molecules are and how many of them I have. Okay? Now A and B are numbers you just look up. So here's the different A's and B's. Okay. Remember, A was about how much they stuck to each other. So helium, being nonpolar, has a really low A. Neon's also nonpolar, but it's got a bigger A because it's got more electrons. and you'll see that that trend goes through all of the noble gases. The more electrons they have, the better that they stick together. And then B is about how big they are. And as you can tell, as the molecules get bigger, these numbers get bigger. The bigger the molecule, something tiny like helium is 0.0237. Something big like CCl4 is 0.138. So that's where we use the numbers. Good news, you don't have to memorize this equation. I will always provide van der Waals equation. And I'll provide the table. You just have to be able to use it and calculate what they ask for. Okay. Now, if you look at this equation, if you don't make the assumptions, if they don't stick together, then A is 0 and this term cancels out. If they don't have any size, like an ideal gas, then B is 0 and this term cancels out and I'm left with PV equals nRT. So it simplifies to the ideal gas law if you make the assumptions. If you don't make the assumptions, then you have to include those terms. So let's try this question. Calculate the pressure of 1 mole of carbon tetrachloride at STP, 273.15 K in 22.4 liter container, both with and without the assumptions. So first let's do it without the assumptions. Without the assumptions, I can use the ideal gas law, PV equals nRT, and they give me moles, temperature, and volume, so I can find P equals nRT over V. And the N was 1.000 moles. R, since they didn't tell me what pressure units they wanted, I'm going to do it in atmospheres. And the temperature, 273.15 K divided by the volume, 22.42 liters. So if you push those buttons, 0.0821 times 273.15 divided by 22.42 times 1, I'm going to do that. And with 3 sig figs, I get, surprise, surprise, 1.00 moles. Or sorry, not moles, atmospheres. And it should be because we've got 1 mole is 22.4 liters, and I'm at 0 degrees Celsius, so the pressure should be 1 atmosphere. Now, what I don't like is that my R is limiting my sig figs. Everything else has got 4 sig figs. This has got, my R only has 3. So this with 4 sig figs is 0.08206 instead of 0.0821. And if you do that, you get 0.9998 atmospheres, which is pretty close to 1. So we got 0.998 atmospheres. Okay, so now let's try it with the assumptions. Okay, so I start sticking in numbers. Pressure observed, that's what I'm trying to find. Plus A. I'm going to find A, and I look up A for CCl4. We saw that just a minute ago. that the A for CCl4 is over here. It's 20.4. So 20.4. And what kind of crazy units do these have? You'll notice it says atmospheres. There should be a line here, so it should be atmospheres. Oh, no, it shouldn't be a line. It's atmospheres times liters over moles squared. So that's atmospheres times liters over moles squared. And I'm going to multiply that by, oops, let's get the question back up. N 0.000 moles over V 22.42 liters, and all that has to be squared, times V 22.42 liters minus N 1.00 moles times B. I'm going to find B for CCl4. And the B for CCl4 was a 0.138, and that's liters per mole. The units are liters per mole. Say that again. 0.138. 0.138 liters per mole. And all of that equals 1.00 moles times R. And since they've got an atmosphere, it's got to be 0.08206 liter atmosphere over mole Kelvin. And the temperature is 273.15 K. So that leaves me with P plus 20.4. Actually, let's simplify this term. So I've got to take 20.4 times, open parentheses, 1 divided by 22.42, close parentheses, square that. And with 3 sig figs, I get 0.0406. And mole squared cancel and liter squared cancel, and I'm left with just atmospheres. That's that term. And then 22.42 minus 1 times 0.138. It's 22.28, and that's liters. And all of that equals 0.08206 times 273.15. Surprise, surprise. That equals 22.41 liters. Ain't going to solve this for pressure, so divide both sides by the 22.28 liters. Oops. Let's check. I think I got the wrong units here. So this had to be moles cancel, Kelvin cancels. Oh, that's got to be liter atmospheres. Liter atmospheres. So when I divide by liters here, I'm left with atmospheres. So where I'm at, sorry, there's not enough room here. It's all just plugging numbers into an equation now. So now I'm at, let's put it up top here, P plus 0.0406 atmospheres equals 22 point, oops, so that division. 22.41 divided by 22.28 is, oops, I multiplied, that won't work. One point 0.005 atmospheres. So that P equals, subtract 0.0406, and you get 0.9652 atmospheres. So the pressure is 0.09625 atmospheres compared to the 0.9998 that we got when we used the ideal gas law. So the pressure I see is a little bit lower than what I should. Okay. So doing these problems is really just identifying the pieces and solving for the variable they asked for. On Schooloop and the Google Classroom, I've uploaded some practice problems. Okay. Work those out. Answer the questions on the form. And don't forget, there you have an opportunity to take a makeup quiz if you missed it, or you can take it a second time to improve your score. And that will be open from 1 to 5 today. The link will be on Google Classroom. Have a great day.